Last time we covered algebraic problems that use trigonometry. In this video, we're going to see applications of trig to geometry problems. Let's start off with the area of a triangle using trig. Area is just half AB times the sine of the angle in between. We covered this in the geometry video as well, the triangle video. Now here we have the law of sines and the extended law of sines. So what does the law of sines state? It states that the side length of a triangle divided by the sine of its opposite angle equals this side length of the triangle divided by the opposite angle and this side length of the triangle divided by the opposite angle. And they're all equal to each other. But not only are they equal to each other, they're also equal to 2 times the circumradius. Now, why is this true? There's a really, really cool proof behind why this is actually true. And the idea is what we're going to do is let's draw this entire diameter. This is the diameter of the right triangle, right? So by our inscribed triangle properties, that's a 90 right there. Now, this is angle A, or maybe let's use big A. That's angle big A, inscribed angle theorem. But then, take a look. Sine of A is sine of big A is A over 2R. So A over sine A is 2R. And then we can do the same thing for B over sine B and C over sine B. They're all going to be equal to this ratio 2R. Pretty cool proof if you ask me. And how all of this randomly connects to the circumradius, that's just a little bit surprising to me. How in a triangle, A over sine A is equal to 2 times the circumradius. Okay, now let's move on to law of cosines. A squared plus B squared minus 2AB times cosine of this angle C. And notice that if cosine is 90, this just becomes the Pythagorean theorem. Okay, and yeah, this was a problem covered in the AMC fundamentals. Okay, now let's explore some examples of these concepts, starting off directly from the AMI. You got a right triangle. PRQ, or PQR. PR is 15. QR is 20. QP, 25. A and B lie on PQ. C and D lie on QR. A and B. C and D. And we've got an E and an F as well. Okay, what do we have here? PA is QB. QC. QC is RD. And RD is RE. RD is RE is PF is 5. Okay. So I think I should flip these, but I think let's flip these. So PA, oh, they're all 5. Okay, I did not see that they're equal to. So PA equal to QB equal to QC equal to RD equal to RE and PF, which you're just gonna have to take them. That is 5, even though it might not seem like it, and that is 5. It doesn't really matter for our purposes, don't worry. So PF, RE, RD, QC, QB, PA, they're all 5. For us to find this area of this hexagon, this thingy. Wow, that's crazy, isn't it? We've just got this random hexagon. Okay, so I'll be complete. This problem is really not that difficult at all. It seems scary. We're trying to find the area of this hexagon. You might be like, area of complex shapes, if you remember that video. You either break it up into pieces. You can break it up into this piece and this piece. That's kind of complicated. Or you can find the area of this triangle and subtract off pieces. The area of this triangle, 1/2 base height. That's 150. Now the area of each of these pieces. The area of this piece is just 25 over 2, half base height. Now what's the area of this piece? We don't know the height. We know the base, but we don't know the height. We know two of the sides, and we have two of the sides. If we knew this angle, we could just use half AB sine C. Do we know this angle? No. But we do know the sine of this angle. Sine of angle Q is opposite over hypotenuse, 15 over 25, 3 over 5. So the area of this, let's color code this. The area of this pink triangle, that's the area of this blue triangle. The area of this pink triangle is half AB. I don't know why I did, oh, yeah. This is it, sorry, and let me make this clear. This is the area of the big blue triangle, 15, 20, 25. This is the area of the smaller pink triangle. Let me do it here. Half AB times sine of angle Q. Angle Q has a sine of 3/5. So that just gives us 15 over 2 as the area of the pink triangle. Finally, area of this, there it is, that area of this purple triangle. And we can do the exact same thing. Half AB times sine of this angle. And this angle is just 20 over 25. 4/5. That's 10. So now all we have to do is 150 minus 25 over 2 minus 15 over 2 minus 10. 120, and that is our answer for this problem. 120, a brilliant problem. Really the key idea, just half AB sine C. Try, if you have the angle, if you can find the angle, you can use half AB sine C. Okay, now let's move on to a slightly more difficult problem, and looks like I've already labeled two of the sides. Okay, we've got this right triangle, right angle B, PA, PB, tan 6, and this angle, APB, equals BPC, CPA. Now, straight off the bat, you're probably like, okay, duh, this angle has to be 120 degrees in order for the sum to be 360 in the triangle. 120, 120, 120. And I'm just going to actually not write this because it's going to clutter the diagram, but you know that each of these angles, these central angles, are really 120, okay? So you might be like, okay, we know this angle, we know this angle, we know this angle. If we knew the side length PC, we would be done. Why? Because we could do half AB sine C on this triangle. We know this angle. We could do half AB sine C on this angle if we knew the side length PC and we know this angle. And similarly on this triangle. So naturally, it's like, okay, let's try and find PC, because then we can easily find the area. Because then we're like, but we don't know PC. What else do we know? Right angle. Okay, that's where we have our aha moment. That's where we're going to get our final equation from. This right angle condition. Final, or equation for x, maybe. We're trying to get an equation for x, maybe using this right angle condition. So what does the right angle tell us? A squared plus b squared equals c squared. We know A? Yes, we do. Law of cosines. A squared plus b squared minus 2ab cosine 120. Now cosine 120 is just negative 1/2. So this is just n squared plus 6 squared plus 10 times 6. This is equal to 196. So AB is 14, the square root of 196. Now, it's actually kind of cool. This might be something worth mentioning. For 120 degrees, because cosine 120 is negative 1/2, this just ends up becoming a squared plus b squared plus ab. So it's kind of like a cool shortcut you can remember. If you have 120 degrees, then you can just write this form of law of cosine. And we're going to actually use that later on, so we don't have to go through the cosines every single time. So BC is the square root of 36, like that. And AC is the square root of x squared plus 10x plus 100. Okay, so now let's just use Pythag theorem. 14 squared plus BC squared, which is x squared plus 6x plus 36. It's all equal to AC squared, x squared plus 10x plus 100. And now we can just cancel out that x squared right there. And we get 196 plus 36 equals 4x plus 100. And we get x equals 33. And that's exactly what we're looking for. Wait, it turns out we're not even looking. I just realized. I thought in the beginning the question, it was asking for the area of the triangle. But it turns out we're just looking for PC. So actually, that would be a more interesting question in my opinion. Finding the area of the triangle. But in this case, it's just asking for PC, and I just didn't even realize that. So yeah, we're just done from here. It's just 33. But just for fun, let's just find the area of the triangle, maybe, just to see. So yeah, we can just use half AB sine C. Yeah, in that case, you would just be like, okay, use a right angle directly. You didn't have to do any of this half AB sine C stuff in the beginning that I was mentioning. But let's find the area of the triangle. Half AB sine 120 is just going to be sine 60 because of our 180 minus x rule. So it's just going to be root 3 over 2 sine of 120. So it's just root 3 over 2 times half 10 6. Root 3 over 2 times half 6 and x is 33. Root 3 over 2 times half 10 33. And we can add all this up. That is going to be equal to 16 times 33. That is 16 times 33 is just 48 times 11. That's 528. So 528 plus 60, 588. So we end up with root 3 over 2 times, that's going to be, what, 294? Right? Yeah, 294. And now that's just 147 root 3. That's our area of the triangle. So, well, let's just look at the key idea here. Really, it's just about x and then law of cosines. It's not that difficult of a problem because you just write law of cosines and then you get an equation. Let's now tackle this very tricky problem from the AMC 12. Circles W1, 2, and 3 all have radius 4 and are placed in the plane so that they're each externally tangent to the other two. Okay, we've got points lying on the circles. They have an equilateral triangle here, this gray shaded one. PI plus 1 is tangent to WI. This is tangent to the circle here. This is tangent to the circle here. So on. We're asked to find the area of this triangle. Immediately you should be like, okay, area of the equilateral triangle, all we need to find is the side length. Now this problem, despite having a very short solution, is actually very, very tricky and hard. But it's a very clever solution if you can find it. The radius of the circles are all 4. And another thing, tangents, 90 degrees. Just mark them straight away. Don't even think about it. 90 degrees, that should be automatic. You should be like at the stage where like, okay, tangent 90 degrees marked. Just no thinking needed to do that. Okay, so we're asked to find this triangle. In general, when you're approaching tricky problems like this, there's 2 ways to do it. 1, look at what you have. Try to make some progress with it. 2, look at what you're trying to find. See if you can find something else that would lead to what you're trying to find. In this case, you always want to kind of explore both directions. In this case, let's start off with, let's try and see what, first of all, let's try and look at reverse. We're trying to find the side length of this triangle. Now, it doesn't really seem easy. I mean, the side length is just this random thing in midair. And you can draw this and try and use law of cosines, but we don't know this angle or this side. That won't work. So instead, let's try to look at the opposite direction. We've got a lot of information we haven't used yet. So maybe let's try and see. We've got a bunch of these radii, right? 4, 4, and then also 4, 4. Okay, so that's definitely useful. It seems like we've got another equilateral triangle here. That's pretty cool, huh? Another thing, geometry problems, look for the information you haven't used. We've used radius 4. Haven't yet used these 90-degree angles we got from the tangency. Can we try and use that? Okay, so first of all, well, this is 60, so clearly this thingy is 30 here. Similarly, we got this is 30 here. This is 30 here. Why? Because equilateral triangle, that's 60. So that part is 30. Change this. 30 and 60. Okay. So how do we find the side length with that 30? Is that really helpful? So let's go back to the reverse direction. Again, we're kind of just keep switching back and forth. We can't easily find the side length of this triangle. We maybe find something else that would lead us to the side length of that triangle. I mean, take a look at the center of this triangle. This is really kind of the tricky step here. So yeah, I hopefully tried my best to explain how you would come with this. You want to try and find the side length of the triangle. There seems to be no easy way to do it with this. So maybe we look inside the triangle. We're like, okay, this is the center of the equilateral triangle. If we can maybe find this length, then we could find the side length. Why? 30, 60, 90s, right? This would be 30, 60, 90 triangle. How do we find that blue length? Well, first of all, we know this is 4. We know this part over here is 30, right? We got our 30, 60, 90s going on. This is 30, this is 30 by symmetry. How about this? That, again, by 30, 60, 90s, is 8 over root 3. Because, this would be 4 over root 3 and then times 2. We got 8 over root 3, 4, and 60. We can easily solve for this using the law of cosines. Aha! That's cool. 4 squared plus x squared minus 2 times 4 times x cosine 60. And you know how I said in the previous problem, I believe, that where you can have this kind of simplification for cosine 120? Well, for 60, it's very similar. It's kind of this thing you can memorize if you want to. You don't have to memorize it. It's not hard to rederive. Just a neat little shortcut here. So you can save some time. A squared plus b squared minus ab. A squared plus b squared minus 4x. That's equal to 64 over 3. X squared minus 4x plus 16 minus 64 thirds. So minus 16 thirds. Okay, and can we just solve for the value of x? You can have to use quadratic formula here. 4 plus or minus, and 90% of the time in geometry problems, it's just going to be plus. Very rarely it's going to be minus. So to decide between plus or minus, just see, okay, which one makes sense in this problem. Obviously, negative lengths don't make sense. So 4 plus or minus square root of b squared, and then we add 4 times 16 thirds. So 64 thirds plus 48 thirds all over 2. No wonder we got radicals going on here. So 64 thirds plus 48 thirds, that's 112 thirds. For 112 is just 4 root 7, so we just take that out. And this becomes 2 plus 2 root 7 thirds. And now that's just this blue length here. We multiply it by root 3 to get this. That's kind of another neat trick I covered in one of the previous videos. We have this and this. You multiply by root 3. Multiply by root 3, we get 2 root 3 plus 2 root 7 for our side length. And area is just root 3 over 4 times that thingy all squared. And you can factor out the 4. Just root 3 times that. This. 10 root 3 plus 2 root 63, 6 root 7. And it's asking for wacky form, so let's just do it in their weird form. 36 times 7, 252. So our answer should just be 552. And that is our answer. Yeah, so really tricky problem, but really nice idea. Key thing, look for 2 directions. Another thing I should just mention, if you have a triangle and you have one side length and 2 angles, law of sines will give you everything you need to know about this triangle. Law of sines, this thing over this angle, which you can easily find using 180 minus. This over this angle equals this side over the sine of this angle, so on. You can find everything about this triangle, all the side length. Now, on the other hand, if you're just given one angle, but given 2 sides, for example here, you can use law of cosines to find this side. And you can even, from there, you can backtrack and use law of sines to find this angle and this angle once you found this side. But it's also true if you have this like this. You can just let this be a variable and then solve like we did here. We had 4 unknown and then this. We just let this be a variable and solved it. So the thing is, one angle, use law of cosines. 2 angles, law of sines. So yeah. And then the key trick here was we want to find the side length. How do we do that? The side length is kind of just this really random length in our diagram. P1, P2, they're kind of like separate from each other, and we're just connecting them. So then the idea is we want to relate it to something we do know, and that is this length here, which luckily we do know because of the fact that we have this length, 4 and 8 over root 3 all in a triangle. It's just a really, really cool solution. This is one of my favorite AMC problems in the last 10 years. So yeah, thanks for watching this video. In the next video, we're going to step it up. We're not going to be real anymore. We're going to the complex numbers in the next video over there.